Hey everybody! So we're still doing some trig equations. We're going to be doing several videos of this, and I'll be generally getting a little more complicated as we go. So I want to do two in this video to try to hit a couple of ideas. So let's just jump right into it. We'll start with that one for tangent. So let me rewrite it. I've got the tangent of theta over root 3 equals 1. So it might be, this is a pretty straightforward equation. It's just sometimes when we're new to the trig functions, they complicate things in our head, right? So this is equivalent to this equation. If I had some variable a, right, and I knew that a divided by the square root of 3 was 1, and I wanted to solve for a, I can multiply both sides by the square root of 3 and get a is equal to the square root of 3, and I'd be done. We can do the same thing over here. Multiply both sides by the square root of 3. Right? Of course, it cancels on this side. And here we get root 3. The difference is now we're just not done. We still have to do the trig part. And like, this is a good, one rule of thumb is you can just sort of, you solve for the trig function and then worry about solving for the variable, right? Remember, we're solving equations, means we want to find all the solutions for that variable. So now we're going to take the inverse tangent of both sides, sort of, and this is what I mentioned in the last video. We're using it in the same way we use the square root symbol when we solve equations by taking the square root of something, both side squares. We don't actually mean the square root. The square root is a single number. The inverse tangent is a single number, but we're going to use this as a symbol to say, I'm going to kind of find where my angles live, and then we'll have to use the geometry of the unit circle to move forward from there. So let's just do it. Theta would be the inverse tangent of the square root of 3. So we're looking for an angle between negative pi over 2 and pi over 2 on the unit circle, whose tangent is root 3, and that turns out to be pi over 3. Okay, so this is the beginning of our answer. So I might put something like, I don't know, I'll put a star to myself, just to let myself know what was like a little asterisk. We're not quite done yet, but we're almost there. Let's think through what else we need. I'm going to draw a unit circle. Well, here's my angle. Pi over 3 is about right here. Now, here's where I like to use something I had mentioned in an earlier video, that one way we can think about the tangent in the definition with the unit circle is, yes, it's the y coordinate over the x coordinate, but that's equivalent to saying it's the slope of the ray of the terminal side, right? Because if whatever these coordinates are, if you take y minus 0 over x minus 0, that's the slope of the line that goes through this ray, because the other point I'm using to compute the slope is the origin, 0, 0, which is just, so this thing is just y over x. So with that in mind, it's pretty easy to see the other place on this circle that's going to have the same tangent is this angle over here. Well, what angle is that? It's this pi over 3 plus pi, right? This is going a half rotation around the circle. Maybe I'll do that in a different color, right? So we're starting from this inverse tangent value, pi over 3. But if we take pi over 3 and rotate half a turn, we get the other angle, right? So pi over 3 plus pi, that's going to be 4 pi over 3, right? But I could have rotated this way, half a circle, right? Or I could have decided to go all the way around once and then landed there, right? So that would be going a half a turn, another half a turn, another half a turn. So 3 half turns in the positive direction. So in this case, what I can do to get these answers is I can keep going a half a turn, another half a turn, another half a turn, another half a turn, another half a turn. Every half turn, in other words, every rotation by pi, every time I add pi to this angle, I get back to a place where the tangent is √3. Or I can go backwards half a turn, okay? So in this case, pi over 3 is my root answer, my primary answer, my base answer, but I can add multiples of pi, right? So k is any whole number, positive or negative, including 0, so our base answer is still there, but we also get all these other answers, okay? So here's an example. Instead of the 2 pi that we added when we had sines and cosines, we just have to add pi with the tangent because you get this repeating, this repetition comes sooner. Remember the graph of tangent. Tangent is periodic just like sine and cosine are, except the period of tangent is not pi over 2, it's pi. Sorry, it's not 2 pi, it's pi. Okay, one more for this video. Let's do this guy. Okay. So here's what we got. This is another example where it's a little ugly to look at, especially when we're first getting used to these trig functions. It might be convenient to make a notational switch and just let the letter A represent cosine of x, right? I'm not really saying anything mathematical here. I'm just saying notationally, it's easier for me to look at this thing if I write that cosine of x as the letter A. Right? And so now I want to solve for A, right? So maybe I'll multiply both sides by 1/2. I get A minus 1 equals √2 over 2 minus 1. I can add 1 to both sides and get A equals √2 over 2, okay? Now, I can do all of the same moves over here. I can multiply both sides by 1/2. So I get cosine of x minus 1 equals √2 over 2 minus 1. I can add 1 to both sides, and I get cosine of x equals √2 over 2, right? So just like what we did with the letter A there, we do it for cosine, okay? You don't have to make this switch, but it might make things easier sometimes, right? Especially when you're first learning this. And you certainly don't have to, if you do make the switch, write out all the steps a second time. I'm just showing you that you can do it both ways and you get to the same result. Now, we're not finished. We still have to take the inverse cosine, again, in that way that's slightly disingenuous. The inverse cosine of √2 over 2 is pi over 4. But again, we'll think of our unit circle. Right, so pi over 4 is an angle about right here. Well, there's another point on the unit circle that's going to have the same x coordinate, the same cosine, and that's if we make the same angle down below. So here's pi over 4, here's negative pi over 4, right? Or you can think about it going all the way around. So 7 pi out of 4, but I like the easiest one. So I see now that I have 2 answers. So let me just rewrite this over here. This was my starred answer. We've got x equals pi over 4, or x equals negative pi over 4. But in the same way that we did in the previous video, or we just did with tangent, except now we have to rotate by a full turn, by 2 pi or 2 pi backwards, we get 2 pi k, where k is an integer, right? Just a convenient way to write down these infinite number. If you really want to be fancy, you can write this whole thing in one expression, x equals plus or minus pi over 4 plus 2 pi k, where k is an integer. Right. The top one with the two sentences is a little more, maybe a little clearer to us, but this bottom sentence means exactly the same thing, plus or minus. So either one of those answers, plus these full rotations, right? So just going to remind us one last time before we finish, this little expression that we're tacking on to the end is a collection of full rotations either direction, right? K is an integer, so maybe K is 1 billion. So that's the answer where we spin around the circle a billion times and then land on pi over 4. Okay, that is it for this one. There'll be more solving of these equations. We can make them more complicated than this. I will see you all next time. Thanks.